So you may have already seen this chemistry cosmetics pack. Some of it's shorthand, some of it's aesthetic, some of it's silly, but it's all fun. Now let's take that even a step further. With some slight modifications, and by relaxing the bond angles and lengths, we gain the ability to sculpt and mold molecular structures while still maintaining their skeletal information. But what good is this? Less talk, more show. Let's get to some examples. Let's look at vitamin C. It's critical for your skin, bones, veins, muscles, and a whole bunch of other things. Without it, these all start to collapse and you get scurvy. This all boils down to collagen, which is a structural support material in your body. It acts as scaffolding and glue. Collagen is a protein composed of amino acids. There are two amino acids in particular that are related to vitamin C here. They are proline and lysine. First, let's look at proline. All amino acids share this fundamental structure. The differences between them are in what you put here where the R is. Add different things where that R is and you get different amino acids. Now let's look at how to draw this in chemical calligraphy. Here we need carbon, nitrogen, oxygen, hydrogen, and a double bond. So intersections are carbon as usual, but terminals are no longer carbons. There are not methyl groups at the end of a line. I can already hear a bunch of you screaming, so let's take a very quick moment to look at why we're doing this. We want the flexibility to sculpt and mold these molecular structures, to contort them and bend them into shapes and forms that could be symbolic or artistic. And by not counting line terminals, the shapes and forms that even simple carbon structures can take are limited really only by your imagination and spatial reasoning. Nitrogen is a loop seamlessly embedded and contorted in any way you please. Oxygen is a circle or any enclosed space deformed as you like. Hydrogens are dots floating around the structure. Feel free to get creative with their shape as well. And double bonds are dots inside of the line. Now let's connect the atoms of our amino group here. The H dot for an OH group can just be drawn right inside the oxygen. You can just omit all the obvious hydrogens, of course. We can shuffle positions a bit without actually changing what is connected to what. That double bond can snuggle right up to the oxygen. That hydrogen in our OH group comes and goes as it pleases. It might not be there, so let's just not draw it right now. And now our little amino acid symbol contains the same information just laid out differently. The video example we're using here was designed as infotainment for an audience interested in cosmetics ingredients. If you're interested in drawing stereochemistry, please have a look at the PDF because we're omitting it in this video. Now let's go back and look at collagen again. It has 3 strands of protein wrapped in a triple helix. Each protein strand is a chain of amino acids. Amino acids have one side amine and one side acidic. The acidic carboxyl side and the basic amine side react with each other, spitting out a water molecule and fusing together. Continue chaining amino acids like this and you have a protein. Now, as for that proline amino acid we were looking at, among all the amino acids, it's rather unique. Other amino acids dangle their side chains outwards. They're kind of loose and wriggly, wiggling all over the place. But proline is unique. Its side chain loops around and connects back to itself, dramatically reducing its wiggliness, while stiffening it up and hardening it to make it a nice strong building block. Collagen acts as structural support and scaffolding for our bodies, so it's no wonder it's got a lot of proline in it. I like drawing proline like this. It looks like a little person holding a nice straight stick. I feel like it represents its role in providing rigid construction material. Let's Bob Ross the proline and turn it into a beautiful little scene with a little happy tree and a sunset. Still contains all the atoms connected in exactly the same way. Or how about this? For you kids out there, this is what telephones used to look like. Or we can just go with fun abstract shapes. Now let's move over to lysine, which provides a different type of structural reinforcement. That long arm sticking out of the lysine reaches out and interconnects the 3 strands, binding them together and regulating their spacing. I'm personally not too fond of counting long chains of carbon in stick notation. It's a little annoying. And that's where this way of drawing carbons has a bit of an advantage. You can make long chains much easier to read. Nitrogen famously likes 3 connections, so we can pull a 3rd connection point out of the loop. In the context of collagen, I like drawing lysine like this. It looks like someone with ponytails using a long string to bind together 3 sticks. You can use chemistry and chemistry knowledge to create meaningful and expressive art. You could draw adrenaline or oxytocin or testosterone or estrogen and draw them in styles and representations that convey meaning and sentiment. Or we can just draw cool stuff. Dinosaur, rawr. Now, after the collagen is made, some of these lysine and proline are going to be modified slightly. Some of them will be turned into hydroxyproline and hydroxylysine by adding a hydroxyl group in specific locations. Now for hydroxyproline, the hydroxyl group interacts with water molecules, creating bridges between the strands. These bridges act like a zipper, tightening the 3 strands and pulling them together. And with hydroxylysine, that hydroxyl acts like an anchor on the outside of the triple helix for sugars to attach to. These sugars primarily help with hydration and spacing. These hydroxyl groups are added by enzymes. These enzymes are massive, tens of thousands of atoms. I'm not drawing them, nobody draws them as molecules. They're great at doing what they do, but every time they get used, they get stuck. And they use vitamin C to get unstuck. This finally brings us back to vitamin C, so now let's draw it. Here's a person holding up a branch with some oranges dangling from it. Here we've got a lake on the right, a forest on the left, and in the middle we've built a greenhouse to house some of the fruit trees from the forest. And my personal favorite, here's a citrus fruit tree with some fruit on the branch and a couple fruits fallen to the ground. And now let's take everything we've looked at today and put it into a single drawing. First, let's draw that vitamin C citrus tree. And standing below the tree, we've got our construction worker with a rigid stick proline, and our ponytailed tying 3 sticks together lysine. We'll add the last details to our tree in a specific way that will be meaningful in just a second here. Now, in the places where we need to add a hydroxyl group to proline and lysine, vitamin C already has hydroxyl groups. Now, there are a couple fruit branches above proline leaning inwards towards the trunk. This represents how adding a hydroxyl group to proline helps create a binding force that pulls all of the strands inwards together. Whereas above lysine, there is a large branch with a tuft of leaves pointing outwards. This represents how hydroxylysine studs the outside of the triple helix with sugars. Finding ways to draw molecules that visually represent their functions can be a bit of a challenge. It's a really fun puzzle. It takes a significant amount of creativity and imagination sometimes, and sometimes you just don't quite find what you want. But even if you don't find what you're looking for, the act of playing with the molecular structures like this will help you absorb some information and maybe even find some inspiration. And when you're tired and worn out from more rigorous activities, this can be a fun and playful way to step back while still engaging with the molecular structures. Or maybe you want to create art and imbue it with some of the beauty and knowledge of chemistry. Anyways, I've been rambling for too long, so hopefully you enjoyed.